For those of you watching the video after the lecture, I forgot to start recording, but you just missed this first couple announcements, so you're good. Just read through those on your own. And now for the fall schedule, the tentative schedule, as I said earlier, I changed some things. Like I pushed back the curved arrow mechanism quiz, I think. Oh no, I pushed back the IR and NMR data quiz. That's right. And curved arrow mechanism quiz is the same. And we still have exam 1 next week on Wednesday and Thursday in lab. And I'll give you more details about that. I'm going to write that exam this weekend, and then after I write the exam, then I like to go, okay, I'll give you like a little summary, like, okay, make sure you're really good at these, these are some of the main focuses of the exam. And then the solubility start date, I think I had that on the Monday or the Tuesday lab, or the Wednesday, Thursday lab, I think was that what I had it at, but I moved it back one. And I'll give you that shortly so you can, pre-lab for that in a couple weeks. Yeah, so keep checking this. I'm gonna probably be moving back the crystallization start time and everything too, because I haven't finished updating that and the rest of these. So more to come on that. And okay, cool. And then this is just some repeats of last time. Join a club, get an extra credit point. Let me know, get an extra credit point, and join up to 3 clubs to get. You can get up to max 3 extra credit points. And then more extra credit, come to office hour, and you can get extra credit. Stay, don't just come for 10 seconds and leave. You have to stay for a little bit. And then even more extra credit, come to the live lectures like now and let me know. I think a lot of you have come, but you haven't let me know. There's an assignment in Canvas for this. So go into there and just say, I came this day. Just give me the date for each lecture you've come, and up to 5, you can get 5 points extra credit. And then, so the extra credit can't hurt your grade. I explained that one before. Homework assignments. I might be able to give the first homework assignment due date, because I may finish chapter 1, and that's what that first homework assignment's about. You want to be starting that anyways, because the exam's next week. Homework problems a lot of them are old exam questions. Initial due dates, you can check them out here. And then initial due dates, you have initial due dates, and then most things you could turn about 4 days late with no penalty. Honors tryout, so that's due today, right? By tonight. I've got a couple that I saw already turned in. So if you're interested in that, turn that in by tonight. And the keys for the course are here. So homework 1, actually the keys in linked here, and it's mostly done, the homework key. I mean, the homework 1, I updated it a tad. So this is a key for the pre-updated. So there's just a few problems that aren't in this key, but I don't even think they matter, because those new problems are like from Google slide animations where you just copy the example. So I wouldn't even really make a key for that. And I like a regular email, like a Microsoft Outlook email, more than the Canvas app email. So if you think of it, send me an email through that. If you send me a message to the Canvas app, it's fine. And then I got a couple chat questions here. Thank you for reminding me, Caitlin, about the recording. I'm looking at the chat here for our unknown NMRs. I can't seem to find a lab guide to go with it under assignments. Oh, it should be. It should be the assignment for the unknown NMRs. It should be under determining the structure of organic compounds. Actually, I'll show you real quick. Let me exit out of this. So if I go to Canvas, assignments, lab, this is the unknown NMR stuff. Determining unknown structures with NMR and IR in person, 20 points. So if you click on this, tells you how you can, upload it as PDF, or you can make a paper copy and turn it in the lab. And here's the link to it. And then when you come into it, it has similar to other labs you've been doing. And one thing that's nice to go to right away is here's a list of the possible unknowns. So your unknown that you have taken an IR of, it's one of these 8 molecules. So question 1 is to actually look up and find the structure of these 8 molecules. So if you do question 1, then you look at your IR, you'll probably be able to figure out what your unknown is just from the IR. And then when you do NMR, you're going to fully confirm it. So this is that experiment. Let's see, I have another question on the chat. For Wednesday lab students, we will be taking the functional group quiz as well as the curved arrow mechanism. So let me see, Wednesday. Oh, Wednesday has not had functional group. You're right. Thank you for pointing that out. Okay, so Wednesday. Yeah, so pre-lab. Wait, Wednesday had the quiz on functional group quiz last week, I think?
No, because the campus got closed, and so we pushed it back.
Yeah, pause share of my screen and look at some. I don't know. Let's see real quick. Grades. You're not going to go see it, but I'll see it real quick. So functional group quiz. Oh yeah, Monday, Wednesday has not taken that. Okay. So functional group quiz and the curved arrow mechanism quiz will happen on Wednesday, today. They had theirs last Thursday, huh? So 2 quizzes for Monday, for today, for Wednesday, people, the curved arrow mechanism quiz and that functional quiz. And then the functional group, or the curved arrows quiz is both Wednesday and Thursday.
And for that one, is it the same quiz that's on the curved arrows link, the little practice quiz? Okay.
And then the IR and NMR data quiz and the PKA data quiz. I'm not sure if I'm going to do both of those next week. Let's see where we get to in lecture today, and I'll let you know.
I actually had one more question. I've been trying to keep up on the due dates. Is there a pre-lab for today?
Yeah. Did you get a pre-lab checked for spectroscopy introduction?
I already turned that in. Wait, no, that one. Oh yeah. I got through 10. I think I'm like halfway through that now.
Yeah, you're good then.
Okay.
Just up to 10 on that one.
Okay.
And actually these pre-labs are just to make sure you get started. And I know, and I said too, these first few pre-labs, I was kind of mixing things up in the beginning of the semester. So I haven't like taken any points away from anybody who didn't quite finish the pre-lab yet. And I'm thinking everybody's moving along good on those. Okay, so back to our chapter outcomes. I'll go about it from our organic chem step by step. So OChem chapter outcomes. Here we are. We talked about calculating octets and formal charges, and that I don't have a quiz for this GSA, but I do have, this is there's part of the homework. And so the next thing we'll talk about is hybrid orbitals. Let me get on my Jamboard here. So hybrid orbitals, I have a nice animation for this. It's down here, online version. So I made this one a little bit, like a couple years ago before I switched over to Google Slides from PowerPoint. So this one's still PowerPoint. I just haven't had time to switch it to a Google Slide. So I've got an online version of the PowerPoint ones that you can watch, or if for whatever reason you're having trouble getting to the online one, I also made a copy of it and I put it on my Google Drive, which you can download like this one. So I'll show you how you download it. Like with the online one, you can just go and try to use it. But the downloadable one here, I'll show you how you do it. You click on it. And then when you get to it, it's not really animatable because it's a PowerPoint file and it's in a Google Drive until you download it. So if you hit the download button right here, see that's like an arrow into a bin. You download it, and then you do have to have PowerPoint on your computer to view it. But if you have PowerPoint on your computer, you can open it and animate it and click through. So I'm just going to kind of briefly go through part of this, then I'll do some more, mostly on the Jamboard. I don't want to bore you just clicking through an animation. You're going to click through on your own later, but I do want to get the basics right out of the bat. So atomic orbitals are and don't feel like you have to write this down real fast. This is available to you. Atomic orbitals are the orbitals of atoms when they're actually all by themselves. So, which is really rare. So like a carbon atom is almost always bonded to other carbons and hydrogens we've been seeing. But if you have a carbon atom all by itself, and that means you have to like heat it up to where it like breaks apart from other atoms and it's in the gaseous phase, a single carbon atom all by itself, it'll have atomic orbitals. And those atomic orbitals will look like this. You have the s atomic orbital. These are actually the valence orbitals. It has core electrons too. Remember, it has the 1s first, and then the 2s is part of the valence. And then it has 2p orbitals. It has one in the x-axis, the y, and the z-axis. So you could think of the x and the y as like in the screen of the monitor you're watching now, and the z is coming out of the plane at you and then away from you. And so it has these 4 atomic orbitals, and they have a certain geometry about them. The p orbitals are all perpendicular to each other, like the 3-dimensional axes. So they're all at 90-degree angles to each other. So here's them all combined. These are all the p orbitals, valence orbitals of a carbon atom. So since they have a 90-degree angle, the atomic orbitals, when the carbon atom's all by itself, gas phase, just a single carbon atom, these orbitals don't really match up with what we need for like the molecular or bond angles that we find experimentally. So experimentally, we find those orbitals when the atom's all by itself, a single atom. But when they bond to other things, like when a carbon, we know when it's bonded to 4 things, it takes on a tetrahedral geometry. And that tetrahedral geometry, it won't work for the atomic orbitals, because see, in a tetrahedron, we know all the bond angles are 109.5 if it's a perfect tetrahedron. But if you look back at the atomic orbitals, these atomic orbitals all have 90-degree angles, not 109.5. So when chemists found like, oh, we see when the atom's all by itself, it has certain angles. And then when we see it in a molecule like this, it has different bond angles that can't really be made from the atomic orbitals. They said, oh, let's call it hybridization. We're going to say we hybridize these atomic orbitals and make them into the bond angles needed for the molecule. So that's the whole hybridization thing. And so if a hybridization, an Sp3 hybridization is where you take the s atomic orbital, the 3 p's, and you combine them to make 4 hybrid orbitals. So do you see mathematically a relationship between the number of atomic orbitals and the number of hybrid orbitals, anyone? Do I have the same number of atomic orbitals added to make this the same number of hybrid orbitals? Yes or no? You can chat it. 4 atomic orbitals. Yes, 4 hybrid orbitals. So however many atomic orbitals you have, think of them as like clay, and you push them all like the s orbitals of sphere and the p orbitals of bell shape, like that double lobe thing. Imagine if they were clay and you just grabbed the clumps of clay and you just mashed them all together, and then you reformed them into these hybrid orbitals. So here's the geometry of the atomic orbitals, s and p. You got in plane, and then in and out of the plane. I use the wedge and dash for that. So if you took all these, if they were clay, and you just clumped them all together, and then you chopped them up into 4 even pieces and then shaped them into the sp3 orbitals, you would have 2 sp3 orbitals in plane, and then 1 coming back and 1 coming out. So, and then we put those sp3 orbitals like this. There's little, we talk about little nubs on the back of these orbitals, these little nubs, but when you put them all together, you can take those little nubs off just to make it more clear. So I've got an sp3 orbital right here. This is one hybrid orbital, this is one hybrid orbital, sp3. They're in the plane. And then I've got a wedge and a dash. And I can say now that these new hybrid orbitals can have the geometry I need, the 109.5 bond angle instead of these are all 90 degrees apart. And then the sp2 hybrid orbital, this one has, it takes the s orbital and just 3 of the p orbitals. It takes the s orbital and just 2 of the p orbitals. So it winds up making 3 hybrid orbitals, and then it has a p orbital left over. So 4 atomic orbitals, 3 hybrids, and 1 left over. And remember, I mentioned it briefly before. The sp2 is used for when we have an atom with 3 things attached to it and it wants to be trigonal planar like this. So it's got the 1, 2, 3 sp2 hybridized orbitals in the plane, and then there's still a p orbital left over, and that's going to be an in and out of the plane version. Does it seem to make sense to anyone that like if I have an s orbital, and then if I use up this p orbital in the plane and this p orbital in the plane, if I use those 2 p orbitals and this s, they would all be in the plane like that, and the leftover one would be the wedge and dash. Does that seem to make sense? So what I'm saying is like, I'm using the s and 2 p's to make these hybrid orbitals. If I choose the 2 p orbitals that are in the plane, then my hybrid orbitals will all be in the plane. And then what do I have left over? The wedge dash. So let me see. Yeah, sp2, and that's just the p orbital. All right. Let me say one other thing too. This p orbital, so it's coming out and going back. This p orbital is it's just one orbital. It sort of looks like 2, huh? It looks like this is an orbital and that's an orbital. No, this is just one orbital.
So Mark, I have a question.
Yeah.
So trigonal planar, you can still have wedges and dashes?
The p orbital is going to be wedged and dashed. Yeah, and trigonal, these sp2 orbitals can be wedged and dashed too. Yeah, I'll actually, after I go through these slides, I'll show you examples of that. And then, oh, here's an actual one of it. This is one sp2 orbital orientation. And if I simplify the sp2 orbitals as just lines and put the p orbital like that, it kind of makes the p orbital stand out a little bit. So this p orbital is actually coming out of the screen at you and then back out. It's like, and it's the geometry of this is actually trigonal bipyramid. Remember how we had the visualizing bond line structures in 3D? So the p orbital is perpendicular to the plane of the trigonal plane, so it's trigonal bipyramid. But I could take and make my, just like your question, the sp2 orbitals and make them not all in the plane of the screen, but horizontal to the screen like this, right? And then our p orbital left over would be an in plane like that. So you can kind of see a little more now how the 2 lobes of the p orbital make a trigonal bipyramid. Or it could be like this, and then those 2 lobes make it. These, since I used these, this is in and out of the plane. This p orbital should be right down the middle. All right, and then finally, sp hybridization. That one's easy. This is for when an atom has 2 things attached to it, so it only needs to make a couple hybrid orbitals, which means out of its atomic orbitals, the 4, it's going to use one. It's going to use the s. It always uses the s, and then just one of the p's. So it'll have 2 p's left over. So that's the linear case. Okay, we got our hybrid orbitals. So if I make these 2 in plane horizontal sp orbitals, I definitely made this with the s orbital. It always has to have s. Which of the p orbitals did it come from? These sp hybrid orbitals, which ones do you think were used? Which p orbital was used to make this? Was it p orbital? Say, we'll call this one. Do I call this one x? I think let's call it x. Z. I forget which one I used before. It doesn't matter. But so let me know in the chat. This sp hybrid or hybridized orbitals, the ones that are in plane like this, did I use the x p orbital to make them? Do you think the z or the y? Okay, good. I'm seeing some X's, more X's. Yeah. And you're right. It was the X. The X was used because it's in plane horizontal. And these were in plane horizontal. If the 2P had been used, then I should draw these like vertical. And if the Y had been used, I should draw them wedged and dashed. So yeah. So I have I have my two sp hybridized orbitals here. And then what do I have left over? I have the Z and the Y p orbital left over, so I can add those in. That's the Y. That's the Z. Oh, that's the Z. So when you hybridize, when you're sp hybridize, you have two sp hybridized orbitals, and then you have a couple p orbitals left over that are set up in a way where each lobe of this creates what shape? What shape is this? Is it a tetrahedron, trigonal bipyramid, octahedron? What do you think? Octahedron, yeah. So if I'm considering each lobe, this is in an octahedral shape. All of these guys are 90 degrees to each other. Okay, and then so here's my sp hybridize again, the first one I just drew. And then I'm going to simplify it and just have the SPs as lines so I can focus on the p orbitals. And be careful here. This is two p orbitals. The gray one is a p orbital and the blue one's a p orbital. This isn't four orbitals. This is just two. P orbitals just happen to be bell-shaped like that. Or is it bell-shaped? I don't know what you'd call that. Double lobed. All right. So if my sp orbitals are this way, hybrid orbitals are vertical instead of horizontal, then I'll have still a horizontal p orbital left over and then in and out of the plane p orbital left over. It would be like that. And if my sp orbitals were diagonal, it would be like that's what I have left over. And notice this is I want you to draw these well. We're going to do these things called sigma bonding diagrams, and I want your angles good. So you notice like right from here to maybe not. That's not the best way to draw it. I'm trying to draw this angle right here, this angle. So this angle right here is 90 degrees, the p orbital to the sp orbitals, and it should be 90 degrees here as well. So from like the sp orbital bonding to this p orbital, that's 90 degrees as well. Okay. Yeah, and then the s and the p orbital are different because the s orbital has no node. So if your nucleus, say you have a proton in here, this is your nucleus, the electrons in the s orbital, they can get theoretically all the way up next to the proton and then out farther. We can do calculations, quantum mechanical calculations. You do some quantum mechanics, and you can find a probability of finding the electron like in here, 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 and all the way up next to the proton. But when you're an electron in a p orbital, there's actually according to the math, there's zero probability of finding the electron here at the node of the p orbital. Zero probability of finding an electron there. But you can find that if there's just one electron in this p orbital, there's a probability of finding it in the upper lobe and the lower lobe, but not in between, which is crazy because that means then it's like Star Trek. It gets beamed across that node. And maybe then Star Trek, like have you ever watched that? How you can beam a person or a thing from one place to another. Maybe it is possible because our atomic orbitals have nodes, and electrons, which have particle properties, they have mass. They can move from one end of the p orbital to the other, but never be in the middle. Also, they've found protons, which are way more heavy, way more massive than electrons, can also have nodes that they travel through. They don't travel through, they just are about. So if there's electrons and protons, and I think neutrons too, then that's enough to make an atom. Maybe we can eventually get atoms and molecules and things through a beam me up Scotty thing. So I think this would be amazing because imagine if you're at like a restaurant, especially when you're on vacation and you don't really have like a big fridge or a big microwave, and you're eating a meal and it's so good, but you got a lot left over and you're not going to be able to eat it and you can't take it with you. you're like, oh, what a waste. So what if they had like a little beam thing where you can like beam it to a homeless shelter or to a poor country that needs food? We could like feed so many more people. This is actually our food production from our farmers who grow the food. It's a very high production rate. And then when we ship that food to market, very high production rate. Selling it at market, it gets lower because sometimes food spoils at the store. But once it gets to your plate, a lot of times, a lot of it's not eaten and just wasted. So it'd be great if we could transport that. And also you could transport all your Amazon goods, like, oh, I need some more pencils, and this shows up on your Amazon teleporter. Be pretty cool. So no, zero probability finding an electron there. I didn't have to write it. It was right here. So with that in mind, and the protons are in here. So the proton is in the node area, and electrons, they're drawn to that proton. Why are they drawn to that proton? Because tell me this, the electrons, what's their charge? Positive or negative? Tell me in the chat. They're negative, yeah. And the protons, what's their charge? Positive or negative? Yep, positive. So the electrons are attracted to the proton because their opposite charges attract. The electrons in the s orbital can get very close to the protons, where in the p orbital they can't get as close because there's no probability of finding it at the proton. So who do you think feels the positive charge pull of the proton more, the s or the p orbitals? Electrons. Yeah, the s. So we say the s orbital, actually we call it more electronegative than the p orbital. So you've only probably heard of electronegativity in terms of atoms, like, oh, fluorine is the most electronegative atom. But now I'm going subatomic. I'm saying the orbitals within one atom, which ones, the electrons within different orbitals, they have different electronegativities. So when we look at an sp3 orbital, it's 1 part s and 3 parts p, right? Because it's like 25% s, because each of the sp3s is made of 1/4 of the s and 75% p. And the sp2 orbitals, they're 1 part s, 2 part p, so they have more what we call s character to them. And finally, the sp orbitals are 50-50. They're each like half s, half p. And you can probably represent that, like if we do our little nubs, make the nub really small for the sp3, that's sp3. And then make it a little bit bigger, like it's got more s character. I think this is the correct way to think of it. sp2, yeah, I think so. And so with that in mind, are the hybrid orbitals all the same electronegativity? Yes or no? No, they're not going to be the same electronegativity, huh? Who's going to be most electronegative? sp3, sp2, sp? Yeah, the sp orbitals would be the most electronegative because they're 50% s, most amount of s character, and the s is more electronegative than p. All right, so I like this trend. sp3 carbons, I say, are least electronegative, and I'm going to actually say they're less electronegative than hydrogen. And that might sound crazy because if you look at most electronegativity table values, they have carbon as more electronegative than hydrogen. But when they have those tables, they're saying like the average carbon, not just sp3 carbons. So, and then sp2 carbons, I say, are more electronegative than the sp3 carbons, like we said before, and hydrogen. And then the sp are the most electronegative carbon. And then I had a question, how do you figure this stuff out? You basically look at like a molecule's reactivity, and if it looks like, oh, this molecule reacts at this atom, and that atom is reacting with like a negative molecule more than this atom, then maybe that atom is positive, that kind of thing. You look at reactivity. And then the, let me see, do I have more here? Then of course, oxygen and nitrogen, fluorine, they're more electronegative than carbon and hydrogen, and much more, they actually big jump. So all of these sp3 carbon, hydrogen, sp2 carbon, they're actually pretty close in electronegativity. especially these two. These guys are still very close. All right, so discard. Okay, so we went through that. Okay, hybrid orbitals. So let's try writing out some examples of this. So I'll just draw up a molecule here. All right, so if I look at this guy, what is the hybridization of this carbon? You can type it in the chat too.
SP2?
Yeah, that carbon has one hydrogen, two other carbons, three atoms. So we say that guy is sp2 hybridized. It's got one secret hydrogen. And you can think of it this way. I'm going to kind of draw it out for us. So this carbon will have an sp2 orbital going this way to a hydrogen, that's S. And then it will have another carbon above that has an sp2 as well, and this sp2, and those two sp2s are overlapping. sp2 here to another carbon's sp2 here. And that's how it does its sigma bonding or single bonds. And these sp2 orbitals are trigonal planar, right? Okay, what about, let's go with this one here. What is this carbon? What kind of hybridization do you think that has? You could type it in the chat. Yeah, it has two hydrogens, two carbons, four atoms. So it is sp3. And we call it sp3 really because it's trigonal, it's tetrahedral. When an atom's tetrahedral, we say it's sp3 hybridized. That's basically how it goes. And if you have four atoms, we say, oh, they want to be as far apart as possible. They want to be tetrahedral, sp3. Okay, and then so that one I can draw, it would look like a carbon with sp2, sp3, sp3, and it's bonded to other carbons here. This carbon is actually sp hybridized. I'm kind of giving that one away already. But we got an sp3 here and there. And then it also has a wedged out sp3 and a dash back sp3. With the hydrogens and their s orbitals. Okay. We're gonna work on next on drawing sigma and pi bonding diagrams. So this is a little bit unclear. You're okay. We're gonna get you good at it. All right. Next up, make that C more obvious. So I'm talking about this C. Okay. What about this one here? What kind of hybridization does that have? In the chat, I'm seeing a lot of sp2. Good. So that's sp. I mean, not sp2. It's a lot of sp. So that one's sp because it has no hydrogens and two carbons. Two things, sp hybridized. So it looks like this. It's got an sp hybrid orbital going this way, sp hybrid orbital going that way, And then it's got another carbon with it that is overlapping with that. So these are the two sp orbitals. This one that it's going down to below is an sp3. That's the one right. I'm talking about this one right here. And the one above it's going to is actually I'm talking about this one. So it's going to another sp2 as well. This is sp2 as well. I mean, not sp2, sp. So this is my carbon of interest. Okay. Let's do linear. Let's see what we're at. So went over. This is kind of like a text version of what I presented. It's probably good for you to read it over again later, see that it makes sense. Okay. No, hybridization. Surprised. I guess you got to do Lewis structures first. Okay, let's look at this practice one real quick here. I like this one. This is a short one. Hybridization practice. Okay, let's get good at this. So hybridization, you're hybridizing atomic orbitals, mixing them together to make new things. And here's a hybridization that's 50% Drake, 50% Napoleon Dynamite. This guy looks kind of like Drake and Napoleon Dynamite. And I love these Venn diagrams. So this is a Venn diesel diagram. So you got Joe Pesci and Dwayne "The Rock" Johnson. And they're kind of combined, they'd be Vin Diesel. And then this one's my favorite. You got the platypus on guitar. I mean, the beaver on guitar. And then you have the duck on keyboards. And then the platypus would play the, what do they call those? Yeah, it's like a guitar keyboard. I don't know. It's funny. All right, so why is an atom with two other atoms attached to it linear? Because they have the nuclei have positive charged protons, the electrons are negative. So they want to be as far apart as possible. So carbon dioxide, for example, which we see in our IR spectrum backgrounds, that molecule is, it doesn't want to be at a 90-degree angle. It wants to be linear, keep those negative electrons as far apart as possible. Lower, and that makes it lower in energy when they're not so close. And we're going to see over the course of the year of OChem, our bonding models are going to be based on what makes you lowest in energy. So the carbon we say is sp hybridized because it just has two things that are linear. When you have three atoms, you want to be trigonal planar. And that again is because you've got negative charged atoms on the outside. They want to be as far apart as possible. So they want to be trigonal planar. When you're trigonal planar, we say you're sp2 hybridized to make you have those bond angles 120. And then when you have four atoms, it could be atoms or lone pairs. So you have like three hydrogen atoms and a lone pair. You treat that lone pair like an atom. They want to be as far apart as possible. That makes them tetrahedral. And so that makes when they're tetrahedral, that makes them lower in energy. And we say that the nitrogen in this case for ammonia is sp3 hybridized. So the nitrogen is bonded to the hydrogen through an sp3 nitrogen hybrid orbital, and the hydrogen's s orbital. And the lone pair is just in an sp3 hybrid orbital by itself. All right, so molecular shape is just we're talking about here is determined by electron repulsion, but energy is the key. We're going to see later that sometimes electron repulsion factors will be overridden by other factors that lower the molecule and energy even lower. But that'll be chapter 15, not for a while. All right, so predicting hybridization. Let's see. Central atom has two atoms or lone pairs. What geometry does it want to take on? You can type it in the chat. You have two things about you. You want to be linear. Good. And then what's your hybridization if you're linear? Sp hybridized, good. How many leftover p atomic orbitals should you have then? If you start with one s atomic orbital and three p's, to become, when you're sp hybridized, that means you have two sps. You use one s and one p to do that. How many p orbitals are left over? Two p orbitals are left over. Good. And what does that look like? It can look like this. If your sp hybridized orbitals are horizontal like this, then your leftover p's are one's in the plane vertical and one's coming in and out of the plane as you in an octahedral type shape. Okay, and then if you have three atoms or lone pairs, what geometry do you want to take? Not linear anymore. What do you want to be? Trigonal planar, good job. And what's your hybridization? sp2 hybridized. And then how many p atomic orbitals are left over when you're sp2 hybridized? So you used up one s and two of the p's. How many p's are left over? One. Yes, good. So what will you look like? You'll look something like this. Boom. If your sp2 orbit orbitals, if one's in the plane and then two are wedged and dashed, you'll have your p orbital in the plane vertical left over. And it's a trigonal bipyramid type geometry. All right, so if you have four atoms and or lone pairs, what geometry do you take? Tetrahedral. And what's your hybridization? sp3. How many p orbitals do you have left over if you've used the one s and all three p's? None left over. So you can draw yourself like that. There's no p orbitals left over. And I'm making a big deal about the p orbitals left over because we're going to see these p orbitals are what form our double bonds or the triple bond. So they're going to form pi bonds for us. We'll see those shortly. Okay, let's practice just stating hybridization right from a molecule. So that carbon right there, what's its hybridization? We'll jump right to hybrid. Well, let's go slow at first. Yeah, you already got it. How many hydrogens, secret hydrogens, does that have? 3 secret hydrogens. So it has 3 secret hydrogens, a carbon below that it's bonded to. It has 4 things it's attached to. It's tetrahedral, so it's sp3, like a lot of you just said already. Oh, I got all this here. I forgot. 3 hydrogens, atoms and lone pairs total 4. Electron geometry, tetrahedral. Okay, hybridization. sp3. There we go. Okay, now with that, this one. Number of hydrogens. How many secret hydrogens does this have? Good, 0. And then how many atoms and lone pairs does it have attached to it? I see the oxygen here, a nitrogen, and another carbon. 3. So what's the geometry if you have 3 atoms and or lone pairs? Trigonal planar, good job. So your hybridization is sp2. Good. Next one, the alkyne carbon here. Number of hydrogens on that alkyne carbon. 0, good. Atoms and lone pairs. 2. If you have 2 things attached to you, what geometry do you want to have them as far apart as possible? Linear. Good job. What hybridization are you to be when you're linear? sp hybridized. You got it. How many, for this next one on the benzene ring, how many secret hydrogens? 1. Lone pairs and electrons. 3, actually. One person put 2, but it's lone pairs and electrons. So it's got no lone pairs, but it's got a carbon atom up above, a carbon atom lower left, and then that extra secret hydrogen gives it 3 total things. So if you have 3 things attached to you, what's your geometry? planar. I don't know why I whispered trigonal planar. You only whisper the secret hydrogens, my bad. And then what about the hybridization? Sp2. All right, we're killing it. What about this oxygen here? We've only been doing carbon so far. We got oxygen can hybridize too. Does oxygen have secret hydrogens? Or no, does it have any hydrogens, this oxygen? No, 0 hydrogen. How many atoms and lone pairs? This one does have lone pairs. Good, I see 4 popping up fast. And then if it has 4 atoms and lone pairs, what electron geometry does it want to have those electrons as far apart, whether they're lone pairs or atoms? Tetrahedral. So then what's its hybridization? Sp3. And I just mentioned the electron geometry. That's where you consider the atoms and the lone pairs. But if you want, I could have added another line. What's the molecular geometry? The molecular geometry would be where you ignore the lone pairs and then it's bent. This is bent molecular. Yeah, good. All right, this fluorine out here, this one's going to be interesting. So this one's it's not an internal atom. It's an external atom. It's just singly bonded on the outside of the molecule. How many hydrogens does it have attached to it? Yeah, no hydrogens on this one. How many atoms are attached to it and or lone pairs? 4, huh? 1, 2, 3, 4 bonds. 1 bond and 3 lone pairs. Not bond, 1 boron and 3 lone pairs. 4. So what geometry does it want? You'd think tetrahedral, huh? Hybridization. So the reason why we hybridize is because when we have an internal atom that we find has a certain geometry through experiments, we say, oh, our atomic orbitals won't fit for that geometry. So we put it, we say it's hybridized. But now when it comes to outer atoms, most chemists will just say it's not hybridized when it's an outer atom, because we say that, okay, this fluorine can bond to the boron with just a p orbital, one of the p orbitals this way, and then it could have its other p orbital and its other p orbital and its s containing the lone pairs. It's sort of unsatisfying, and if you decide to say, because some chemists will say, let's just say they're hybridized. So some chemists will say, oh yeah, this fluorine's tetrahedral is trigonal. I'm sorry, they'll say this fluorine is Sp3 hybridized, and these lone pairs are in the Sp3 orbitals. But the majority of general chem textbooks and chemists will say, oh no, it's unhybridized when it's an outer atom. So it's kind of a weird one. I don't really care. It doesn't really matter that much because you don't have another atom to attach to fluorine and have to know the bond angle. Those lone pairs are just on the outside. So don't worry about outer atoms. You could just say they're always not hybridized. But if you did call them hybridized, I won't mark you off for it. All right, but the boron here, that's an internal atom. Yeah, boron's an internal atom because it has more than one other atom attached to it. Fluorine's an external atom because it only has, it's bonded to the outside of the molecule. It's not, there's only one atom bonded to it. It's not bonded to 2 or more. But boron's an internal atom, so it can be hybridized. So it's got 3 things, or let's see what it's got. Any secret hydrogens? They don't do secret hydrogens on boron. So how many hydrogens does boron have? 0. What about atoms and lone pairs? It's got 3 atoms, no lone pairs. Electron geometry. Ooh, I gotta fix that box. It's gonna be trigonal planar. Oh man, my text box got messed up. Hybridization for this one. Sp2. Is this the online version? Oh yeah. Oh, this was a PowerPoint. I switched over to Google slide animation. That's why it got messed up. Okay. What's with the extra dot there? Oops. Oh, I know what's going on there. This box has to increase. There we go. Okay, sorry about that. Okay, so there we go. And then as you're clicking through my animations, this summer I had the idea to make it like binge learning. So if you wanted to binge on, you can go to the Lewis structures, dipole moments in resonance. And then this one I like because the Lewis structures is named after the chemist Gilbert Newton Lewis. I think his parents named him after Isaac Newton. And so I thought it was funny that Fig Newton's a joke. If you've ever seen Talladega Nights, it's a pretty funny movie. Billy Bob. If you're not first, you're last. So done with that one. Let's see, where am I? Okay, we've gotten really good at the hybrids and stuff. And what I'm going to do, I'm going to take a break. And I'm actually not going to go through the bond line structures. Bond line structures in 3D? No, not that one. I'm going to let you do this one, the Lewis structures and dipole moments. I spent a lot of time on that this summer, and it's a really good one. And Lewis structures is really a general chem subject. So I'm going to let you guys go through that, and I'm going to skip ahead to the sigma and pi bonding diagrams. Yeah. Perhaps I'll just do one example. I'll do one example of this, and then I'll skip ahead to the sigma and pi bonding diagrams. I don't have an animation for that one. That's the next thing I got to animate, come up with an animation for. But before I do that, let's take a break. I was looking over my Lewis structures Google slide animation, which am I sharing my screen? I am, huh? And this was a long one. I thought it would be quick, and then I was like going through it, and then just thought, oh, okay, I should do another example. And then I'd be like, I'm done. And then I'm like, no, I should do an example like this. Oh, they need an example like this. So this is a long one, and you should go through it. It's part of the homework one. It says to do it, I'm pretty sure, right? Let's double check. Homework one. I think I added in. So here's a homework one. It's got some practice drawing the p orbitals that are left over for hybrids. And here it is, a bunch of GSAs in the homework. So like it says, write out all the examples from this one. Yeah, Lewis structures, dipoles, and resonance. So you'll go through that as part of the homework, and then as you go through the examples, which I'll show you here. As you go through the examples like this one, you'll just write them out on paper or on your tablet or whatever, kind of work along with them as you click through them. And now I'm looking through it myself now because I want to make up an example that's not present in here and work on it with you. I do like that one. I'll do it with, I'll do an enolate. That'll work. Okay, let's do it. Before I start that example, do you have any questions?
Hey, Mark, I do have a question. It might be really off topic, but so you know how trigonal planar is Sp3 hybridized?
Yes.
Right?
Yes.
So how would I, and they still have wedges and dashes, right?
They
With
could.
trigonal planar. So how would I know to draw out my wedges and dashes versus just that example where they're all on the plane of the page?
Actually, we're gonna, after I do this Lewis Lewis structures and dipole moments in resonance, then I'll do some of this sigma and sigma and pi bonding diagram, and it'll answer your question. So let me do this one first, though. But good question. You'll see.
Because like I'm confused with like the terminal atoms on the end. You know what I'm saying? Like
I think so. And when I'll do a couple examples of that right after this one. Good question.
Okay.
All right, so this one. So in the Google slide animation of this, there's a lot of examples, but I'm just going to do one now for you, and then you'll have lots of practice in there. So I'm going to do what we call an enolate. I'm waiting for my Jamboard to wake up here. Come on. Oh, wait, I think I know how to make this work faster. I believe now if I plug in my iPad to this, I might be able to get on the wired internet in my office. Let's see. There we go. Maybe it's working. Cool. Okay, so the example I'm going to do is it's called an enolate. Let's go CH3 CO minus. This is a funky one. Wait. No. I'm doing this wrong. CH3 CO CH2 minus is what I want. So in the Google slide animation, I do start off making these Lewis structures by following the real careful rules about them and go real slow. And then after a while, I start showing you like kind of shortcuts, how to just kind of speed ahead. So I'm going to do it in like a shortcut manner here. So this guy, what it should look like, I'll do the structure of it first. So it should have a carbon with 3 hydrogens on it, a carbon in the middle, and then another carbon at the end. And then this, I won't jump right to the double one. This carbon's got an oxygen attached to it and another carbon. And then this carbon's got 2 hydrogens on it. And if you count up the total number of valence electrons, let's just do that really quick for this one. So for the carbons, we have how many carbons? 3 carbons. So it's 3 times, they should have 6. I'm sorry, 4. And that's 12. And then for the hydrogens, there's 5 hydrogens times 1, that's 5. And then the oxygen, there's 1 of them times 6. That's how many valence electrons it has, 6. And then there's a charge to this molecule. And the molecule has a negative charge. So what do you think that means? Does that mean I need to add an extra electron or take away an electron? You can type it in the chat. Since it's a negative charge, you have to add 1 electron plus 1 electron, because a negative charge means you have 1 more electron than your number of protons in the molecule. So it's more electrons. Seems weird to add 1 for a negative, but that's what it is. So we got 1 there. So total valence electrons for this molecule is 11. That's 11, 12, 24. Okay. So how many valence electrons have I used so far in just connecting my atoms with single bonds? I got 1, 2, 3, 4, 5, 6, 7, 8 bonds. And they each have 2 electrons. So I'm going to say minus 16 electrons for single bonds, which leaves me 8 electrons left over. And the way you're supposed to fill these 8 extra electrons in is fill the outer atom octets first. So this oxygen, I'd go 1, 2, 3, 4, 5, 6. So its octet's full. And now I got 2 carbons that are internal, but I'm going to put it on the more outer one. Yeah, that's not so obvious that I put it on that carbon versus the middle one. But oh well, that's where it goes. So now for this example, if we get to this point, we try to calculate formal charges in octets and see if we need pi bonds. So for instance, this oxygen here, does it have an octet? Two, 4, 6, 8. Yes, it has an octet. It's got the octets, happy. Now, what about its a formal charge? Does it have a formal charge? So it's group 6 minus 1 bond minus 1, 2, 3, 4, 5, 6 lone electrons. Yeah, minus 1 formal charge. Okay, now to this carbon in the middle. Does it have an octet? 2, 4, 6, no octet. It's going to want a double bond, so it can have an octet. Does it have a formal charge? So it's in group oxygen, carbons in group 4, minus 3 bonds, minus no electrons. Yeah, plus 1. Yeah, this is definitely wanting to have a double bond, huh? It's got no octet, a positive formal charge. And then what about over here, the carbon on the right? Does it have an octet? 2, 4, 6, 8. Yes, it has an octet. So it's satisfied in terms of octets. What about a formal charge? Does it have a formal charge? It's in group 4 minus 1, 2, 3 bonds minus 2 electrons. So it's 4 minus 3 minus 2. Oh, that's minus 5. That's going to be a minus 1 minus charge, minus 1 formal charge. So it's going to want some pi bonding too. Okay, so now this is what I would call our preliminary Lewis structure because it's got a lot of charge on it. And I think this is going to be like not really a major contributor to the actual molecule. It's just like a beginning preliminary Lewis structure, not one that we really think of as anything major about it. It's like the ultra minor resonance structure. And I can double check that I've done things right so far by making sure my formal charges should all add up to the charge of the molecule overall. So my formal charges, I got a -1, +1, -1. That all adds up to -1, and the molecule should be -1. So that's looking good. Okay, so now what I want to do is I want to add a pi bond. The first one I'll draw is dropping the lone pair from the oxygen down to that carbocation, we call it, the carbon with the plus charge. That's going to be now, this is like our, this is, I'm actually type it over. This is called this our preliminary Lewis structure. Preliminary Lewis structure, and then okay. Now let's draw like, now this is this resonance arrow we're doing here. It's going to get us to like our first real resonance structure here. CH, C double bond O. See how my central carbon now, it gained that pi bond, and it no longer has a formal charge. Now it has an octet and 0 formal charge. I can tell that it has an octet because I just go 2, 4, 6, 8, and so it's an octet and no formal charge. So that really helped out having that pi bond. The oxygen up above, it went from having an octet and a negative charge to now, does it have an octet? Let's see. 1, 2, 4, 6, 8. Yes, it does have an octet. And actually, I was drawing octet in green before. Let me do it in green, like it's green light, go kind of thing. So octet, no formal charge. And then here, octet, and then no formal charge. Let's see, group 6 minus 2 bonds, 4 electrons. Yeah. So that really helped, that pi bond for that guy. But then this poor carbon down here, it has an octet, but it has that minus charge still. It doesn't want that minus charge. So what do we need to do about that? What do we draw next? Does anybody know? I randomly, kind of semi-randomly drew the oxygen forming this double bond. I could have had the carbon. What's that?
Sorry, would we show that carbon on the right getting the double bond?
Yes, that's right. So what do we call that when we do that? Do you remember the term? We use this double-headed arrow.
Resonance.
Yeah, we're gonna draw resonance. And Annalise had a question. Doesn't the overall molecule need charge? So the overall molecule does have charge in these. I think what you're asking is, should I be drawing like brackets around it and saying like -1? A lot of teachers teach that in general chem. We're not going to do that in our class. We're just going to show the formal charges and know that they add up to the overall charge. I think that's what you're asking. Okay, so now, okay, well, this is what's going to happen though for the resonance. This lone pair from the carbon is going to come down and make a pi bond. Then the pi bond and the oxygen is going to go back and make a lone pair up there. And it winds up when we do that, the carbon will, on the right, will lose its negative charge and keep its octet. Now it still has an octet and no formal charge. So it got happier with that resonance, right? And so resonance is just a tool we use to try to show how bonding is in a molecule. It's not the reality, really. It's just the it's going to help us know that, like, oh, this carbon has most of the negative charge and the oxygen has a lot. Oxygen and the carbon have the negative charge of this molecule. Like this carbon on the left doesn't really have negative charge. So that's what the resonance helps us out to. And also the carbon in the middle, not a lot of negative charge there. But what we do then next, after we do draw the resonance structures, is we draw resonance hybrids. So let me actually snip this out, see if I can show you that on the next panel. Ooh. Now I'll draw the resonance hybrid. So a resonance hybrid is basically, you take the resonance structures, the main resonance structures. I'd call these two the main resonance structures, like see how at the beginning I forgot. This was the preliminary resonance structures. These are the main resonance structures here. Edit. Okay, so we got our main resonance structures there. We'll take those main resonance structures and we'll combine them into a hybrid. And the hybrid is more like reality, what we think the molecule really looks like. So this is how, but before I do it, I need to also look at these two resonance structures and ask myself, are these two resonance structures equivalent? And if they are equivalent, or we call them degenerate in energy. Let's say degenerate. Degenerate sounds like a bad thing, like you degenerate, just hanging out in the corner getting in trouble. But degenerate in this case means same. So are these two the same? Like, do they have symmetry? Are they like the one on the left, you have a double bond to an oxygen, and the one on the right, you have a double bond to carbon? Are they the same or different?
Is there one that we prefer to draw more of, or is that why we draw the, does it not matter? Is that why we draw the hybrid?
So, but do you first tell me, are these two the same or different? What do you feel? Yeah, they're different. They're not the same. If they were the same, an example of the same would be like acetate, the most common like resonance. So let's look at that really quick. A little sidebar here. Oh. Here's acetate. You can see like, oh, I'll make the pi bond there, maybe there. These two, each resonance structure is exactly the same. These are equivalent. Ooh, T equivalent. Degenerate. Okay. Because they both have a double bonded oxygen, a single bonded oxygen with a minus, double bonded oxygen, single bonded oxygen with a minus. So, but these are different. And so they are different. And when they're different, you have to decide which is the major resonance structure. Okay, so Alina, yeah, that's true. You can say they're different because they have the negative charge on different atoms, and also different atoms have double bonds. They like the lower right-hand corner one. They have to be, everything has to be the same to be degenerate. Okay, so when different, my eye is bugging me there. Different, like, okay, so I'm gonna say my typos in lecture don't count for extra credit corrections because it's just too hard for me not to do them. Look for typos though in like the Google slide animations, things like that are used over and over. All right, so the major resonance structure, what is the deal with that? Is what the actual molecule looks more like. Stable. All right, so so the major resonance structure looks, the molecule, it looks kind of, the actual molecule looks kind of like this left resonance and the right resonance, but it'll look more like the major. So how do we determine major? So to determine the major, you first say, you look at octets. Possibly major. You want to have octets. And then the second thing you look at is formal charge. I have to say first. Second, look at formal charge. Want positive charge on less electronegative atoms. And negative on more. But you look at that after octet. So if you look back at this guy, the oxygen up above, all octets, the carbon, all octets, everybody, this carbon, all octets, everybody has an octet. On this one, octet, 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 octet. Everybody has an octet that wants an octet. The hydrogens, they don't want an octet. They want what's called duets, just two. So they're happy to. So both sides, all octets, both resonance structures. Octets and duets. Okay, so they're tied at that first check. Now, the next thing we would check is negative charge. So the right structure, the formal charges, the left, I'll say the left has a negative charge on a carbon, right? And the right one, negative charge on the oxygen. So which atom do you think can handle that negative charge better, carbon or an oxygen? Whoa. Oxygen. And why the oxygen? It's more electronegative. It's more electronegative. That means it likes to pull electrons to it more strongly. So that suggests that, oh, it doesn't mind having extra electrons at negative charge much. So with that in mind, what's our major resonance structure? It's going to be the right one. We go. Now we know that what the major resonance structure is. We can draw the hybrid, and we'll say the hybrid looks more like that one. So let's do that. Let me go to a new panel here. Boom, boom. And I'll say this one's the major resonance structure. Okay, and the way I draw the hybrid is the following. I draw out all the atoms with single bonds, all the single bonds first. And then I draw dots for the pi bond that's being shared between the two things. Like that. And you notice how I drew the dotted pi bond. I do it maybe a little different than, oh wait, you're not seeing it yet, are you? Oops. Sorry, my Jamboard was slow. So, oh, come on. So I wind up drawing that on the wrong page. Okay, back to it. So here's my hybrid. I'm on that panel. Yes. Okay. Oh, I always want to put an E on hybrid. Hybrid. Okay. So I draw in all the atoms that have single bonds. And then I draw dots to represent that shared pi bond. And you'll notice I started my dots. If you've done hybrids before like this, you might not have done this. I start my dots on the atom, not just between. So it goes up to this oxygen. The way I like to think of it is this oxygen, when it sometimes we have the one resonance structure where the lone pair is on it. So that's like representing when the lone pair is on it. And then the carbon also has a lone pair on it sometimes. So if I dot it all the way over to the carbon, then it's showing that that pair of electrons shared as being on each atom and in between them. And then also you'll notice my upper oxygen here, it has 2 lone pairs and 3 lone pairs. So it always has 2 lone pairs. So I put the 2 where the carbon doesn't have a lone pair all the time. So I don't add a lone pair. So that's my hybrid. And then I need to add my charges. So the molecule has a -1 charge overall. Do you think each atom, the oxygen and the carbon, then have -1/2 charge? No, you're right. So I'm going to say the oxygen can hold more negative charge. So I'm going to say it's like, I'm just going to guess at this number. I don't know for sure this, but I'm just going to say there's more negative charge on the oxygen than the carbon. Because my actual molecule, my hybrid, should look more like the major resonance structure. Okay. More negative charge on the more electron. Negative oxygen. And I'm not sure it's 2/3 and 1/3, but I'll just use that as an estimate.
Dr. Springsteel,
Yep.
I'm a little confused. Is the oxygen on the hybrid supposed to have 3 lone pairs?
Well, the oxygen on the hybrid, it should have 2 lone pairs. And then sometimes it, like if you think of it from the resonance structures, it always has 2 lone pairs. See that on the left resonance structure, you got 2 lone pairs?
Yeah,
And on the right, it has 3 lone pairs, right?
yeah.
So what we're saying is that pair of electrons right here, this pair of electrons could be as a lone pair or as the pi bond. So that's why I showed as dots.
Oh, okay. Thank you.
Mhm. Okay, and then now once we have a hybrid, we can draw it in 3D. So let's draw it in 3D and then draw these bond dipoles and stuff. So I'm going to do this one kind of quick. This has really worked out well in the Google slide animation that you'll go through for the homework. So panel 5, come on, board. I'll finish with this. I was going to do sigma and pi bonding diagrams today, but I didn't get to it. I didn't have enough time. That's okay. We'll do that next period. And yeah. Let me, my internet is not going faster. Okay, here we go. Finally got that up. Okay, so now I'm going to draw it in 3D. So I want to draw my longest chain of atoms in the plane of the page. And if I number these, it would be like the carbons. I'll just number 1, 2, 3, 1, 2, 3. And I know the first carbon, it's got 3 atoms. I'm sorry, 4 atoms. It's going to be tetrahedral. And my wedge and dash got to go down. And then my oxygen is going to be, the carbon in the middle is going to be trigonal planar. So I got to draw it like that. And then this carbon 3 is going to be trigonal planar too. So there we go. We got it in 3D. I'll draw the hybrid. So say like minus, it's about minus a third, minus 2/3, something like that. And now, oh yeah, we're gonna do bond dipoles. So bond dipoles, there we show arrows to represent them. The positive end, we put a plus sign on, and then the arrowhead is the negative. So this is the plus side, and this is the minus side. So carbon and hydrogen, they're so close in electronegativity that you can kind of just ignore the bond dipole. Dipole, dipole is insignificant. Carbon-carbon, the same thing. So let's just ignore those. But let's draw in the ones that count. The carbon to oxygen is definitely going to have a bond dipole towards the oxygen. And then the 2 carbon-carbons and the rest. So that's, yeah, those are all pretty much insignificant. So this would be my bond dipole diagram. And then my molecular dipole is going to be the same thing, because it only has the one. Usually you have more than one bond dipole. So let's just put molecular dipoles like this. Okay, so I know I kind of went fast through that one, but I wanted to make sure to get at least that done. So for chapter 1, all we have left is sigma and pi bonding diagrams. And I'll do that on Monday, and I'm going to decide whether I add that to the exam on the Wednesday, Thursday. Kind of want to. Yeah, maybe I'll introduce that in lab. This way we can get it on exam 1. I want to get all of chapter 1 on exam 1. So maybe I'll do that in lab today. Today and tomorrow. I'll just get it done. I think I will. Yeah. So exam 1, as of now, it's going to be chapter 1. No, it won't have chapter 2 material unless I'll let you know on Monday if I change my mind. If I add any of chapter 2, what I do is if I happen to decide to add something last minute to an exam, what I do is I make it this super obvious question, like kind of the obvious quizzes, where you have the key before.